Hello everyone, welcome again to chapter 3, which is about the formalism of quantum mechanics. In this chapter we will discuss, we can say, the theory or the abstract of the quantum mechanics, and we will justify a lot of things in a mathematical and rigorous and also beautiful way. So we can think of this as the linear operator or the algebra of quantum mechanics. So in quantum mechanics, we studied two objects. The first object, that the state. We started with the state, or we can call it the wave function. But I am on purpose, I don't like to use the word function. And also we have the observables, the thing that we measure, or the thing that we can associate with measurement in the real experiment, which can be studied through the linear operator on, I forget here, on Hilbert space. Hilbert space. So the state lives in Hilbert space. Hilbert space, we can think of it as an inner vector, as an inner product and vector space. So we can define an inner product in our vector space. This just for now. Of course, it has some additional properties, but we don't care about it. So we have these two objects, with the state and the observables, which can be described by the linear operator. In particular, we have two main Hilbert spaces in quantum mechanics that we usually deal with. The first one is basically the Cn, which is basically you have a vector which consists of n elements or n component, and each component is a complex number or could be a complex number. This is the first main Hilbert space. The second one, which is the square integrable function, and we have seen them a lot in chapter 2. Basically, when we have, for example, sine or the exponential or whatever. So these are the square integrable function, which sometimes called L2 function in functional analysis, for example, course. And the set of, so how we can define the square integrable, just for the sake of this course, it's enough to know that this is the set of all function such that this quantity, which is the square of it, is finite. Of course, from this property, we can also deduce one main thing, that if the function f, or the absolute value of f squared, goes to 0 as we go to infinity. Plus or minus infinity. And that can be seen because if this is not finite, so if, this does not go to 0, for example, goes to a finite number, let's call it k, so this integral will go to infinity. So this is just one result that we'll use in the future. Now we discuss what is the observable. So let's say, or let's assume that you want to measure quantity. So a measurement quantity that you go to the lab and you measure it. For example, the momentum, okay? Or let me make it general and I will call it Q. So some quantity, the speed, the kinetic energy, whatever. As we said previously, that each observable or each measurable quantity, we can connect it or we can associate with it an operator. Now, the average of this quantity, so if we measure it many times at the same state, so we have one state and we measure it many times. We discussed this, I believe, in chapter 1. So the expectation value of this observable is defined as following. You take, first of all, you apply the operator on your state, then we take the inner product with the state. So this is the definition of the expectation value. So first, we apply Q, which is the operator, which corresponds to the observable that we are interested. We apply it on the state, then we take the inner product with the state, okay? So this is the definition of the expectation value, where here the state is in our Hilbert space. So let's start from the first fact, that the average or the expectation value must be real. What do we mean by a real? By definition, a real number, it is if and only if, so we said x is real if it is equal to its own conjugate. So for example, 5 is equal to 5 conjugate, but I does not equal to I conjugate. Or for example, 3 plus 5i does not equal to 3 plus 5i conjugate, etc. So of course, this is something that we impose, that the expectation value must be real. It doesn't make sense that we calculate something in the lab or in the experiment that we get a complex number or imaginary number. So from here, from this assumption, show that Q must be Hermitian. And that's simple. So Q, by definition, what we say? We say that first you apply the operator on my state psi, then we take the inner product with it. Now we know that the Q conjugate is the conjugation of this quantity. But from the property of inner product that we study in the linear algebra part, we know that is equals to, if I just flip the order, so I flip the order, so I'll take Q psi Q. So we know that we deduce, since both these quantity are equal, so this and this, they are equal, we deduce that is equals to. But this is true for all psi in my Hilbert space. Now, one property that we didn't show it, that if you have this holds for all function in your Hilbert space, then we can deduce that for arbitrary function, another function, let me call it function f, and q and g is equals to q f g for any f and g in my Hilbert space. So this property, maybe I believe it's an exercise in the book, but it is easy to show, but it takes time, and that's why I skip it. So it's very easy to go from here to here. Now we have this, but we know from the definition of an operator, we call it Hermitian if satisfy this property, or we can say that, if you want, that Q is equal to Q dagger, or the conjugate of my my operator. And here we can say this is a proof or a demonstration that why in quantum mechanics we must have a Hermitian operator or a self-adjoint operator. It's because it started from here, that the average quantity must be real, otherwise it doesn't make sense. It is not a physical theory. Now we discuss about special states, or a state which has a deterministic property. So let's assume that we have a state, I will call it for now phi. So this state, as we said, it lives in the Hilbert space, such that if we prepare our experiments at psi, so for example, each time we prepare it to be at psi, and we measure Q, so Q is just a quantity that we measure, either the momentum, the position, the kinetic energy, whatever, we get some quantity called Q0. Q0, this for example could be 5. So for example, let's assume that I always prepare my state at, or my experiment at state phi, and I measure, for example, P, the momentum, and I always found it to be at 5, which is, in this case, is Q0. So that means the average or the expectation value, of course, should be Q0. Moreover, that means that the standard deviation, of course, becomes 0, because each time I calculate it, remember, what is the standard deviation? By definition, it's how your values are separated from the average or the expectation value. But each time I calculate, I get Q0. So that means the standard deviation is equal to 0. So this quantity is equal to 0. So far as I believe most of these you are familiar already from chapter 1. But here's a crucial thing, that this standard deviation, it can be written as, just let me go here, jump here, and I will get back to the derivation. So it can be written as a Q, where Q here is the operator, minus the average square. The whole thing is square. So we can think of it, this is the original definition of the standard deviation, that how my quantity is far from the average, we square it and we take the expectation value. So this is the meaning for it. But we can show it mathematically very easy. So we start from this expression, which is the standard deviation square. So this is sigma square. And then we notice this expression is basically equal to this expression. If you want, just distribute. So we know that the expectation value is linear, so we can distribute it to the first term, to the second term, to the third term. So let me just do it here quickly. So if we distribute it to the first term, we get the expectation square, so this is the first, minus, notice this is the average, is just a number, so we can take it outside. So we have 2q, then we take the expectation value of q, then plus, now the expectation value of a number, just basically the number. So we get q, the whole thing is square. Now if we simplify this expression, you will get back to this equation. So it's basically the algebraic manipulation, very easy algebraic manipulation. Now why we rewrite it in this term? Because we can, first of all, we can apply the definition of the expectation value. Remember the expectation value, we can call this, for example, call it t. So it's an operator t. So we are taking the expectation value of the operator t, which is equals to psi, then t at psi. Okay, this is what we have done. So this, if we can call it t. Here t is the whole thing here squared. Now we use a crucial fact, which is, we know that q is Hermitian. So the fact that we're using that q minus some scalar is Hermitian. And I believe this is very easy. I will show it quickly. So we know, so how to show that it's Hermitian. We start from, so this is, when we apply it on, for example, a function f, and we take g. So my goal is to move this operator to the other side without taking the changing this operator. So this is by definition what do we mean by a Hermitian. Now we can distribute. So I will distribute this to the function f. So I will get q f minus q0 f on g. Okay. But if we apply q and f, sorry, if you distribute, so we get qf g. So I'm using the linearity of the inner product. So I'm distributing this to this and to this, minus q0 f g. Now we use two facts. The first fact that q is Hermitian, and the second fact is that the number, the scalar q0 is of course Hermitian. Any scalar is Hermitian. Very simply you can show it. So the first fact, which is q is Hermitian, so we can move it to the other side. So qg, something like this. And the second fact is that q0 is also Hermitian, so we can move it to the other side. Then now we can combine. So we use again the reversed linearity. So f q minus q0 g. So it's very simple. We show that indeed this operator, which is q minus q0, is Hermitian. So now we have a square of it. So we apply it twice. So now we can move one of them at the other side without doing anything because it's Hermitian. So basically what we are using the fact. If you have, and let's assume that t, the operator t, is Hermitian. So we apply it twice on f, right? Now I can move this because it's Hermitian, the one on the left, here. So I can have something like t psi tf. Okay. So I'm using the fact that t on the left is Hermitian because I have two of them. So we know that q minus q0 is Hermitian. We can move it to the other side. We will get this equation. But remember, this basically is the standard deviation square, which we said that is equal to 0. But now we have the inner product between two vectors. So we can see it as the inner product between v and v, where v here is a q minus q0 applied on phi. So it's equal to 0, but we know from the property of the inner product this is equal to 0 if and only if the vector v is equal to 0. That means the whole thing here is equal to 0. So we have it here, it's equal to 0. Now if we simplify, or if we move this to the other side, we get this is the equation. Now, what's the physical meaning of this equation? The physical meaning is the following. We apply the operator q to specific state, which is the special state, I call it, and we get some scalar q0 times the state. So we study this in the part of linear algebra. q0 is an eigenvalue of a q. Eigenvalue of a Q, which is of course it has no problem so far. But the second part, that psi itself, phi, it is an eigenfunction of a Q, capital Q, of the operator Q. So what does that mean? So that means that the state with the deterministic measurement, so any state that we can every time we measure it, we get the same value or the same quantity, so the standard deviation is 0, are the eigenfunction of a Q. This is an essential and important idea in quantum mechanics and in the physics of quantum mechanics. So what do you mean by a state that it has deterministic measurement? That means it must be an eigenfunction of the operator. So for example, if you have a state such that it has a deterministic momentum, so that means it must be one of the eigenfunction of the momentum operator, and etc. Okay. So as I said here, fact, this state, which are the eigenfunction of a Q, are complete, so they span Q. This is another fact, and I will stress it again and again, that the eigenfunction of an operator, so if you have any operator, for example, T operator, any operator you think about it, so if we have the eigenfunction, so we gather the eigenfunction, these eigenfunction span my Hilbert space. What does that mean? That means any state we start from psi can be written as a linear combination of these eigenfunction. Okay? If you remember now, or if you noticed, what we are doing now is just generalization of what we have done in chapter 2. In chapter 2, we start with an eigenfunction of the energy or the Hamiltonian operator, if you remember. Okay, we'll revisit these, but now try to think of it as general as possible. So if the eigenfunction are psi1 up to psi n, we are assuming here we have a discrete of them. So any function in my Hilbert state, in my Hilbert space, any function that you think of it can be written as a linear combination of these. Or we can, if they are not discrete, we can just write them integration. So this basically is just a continuous version of this. Now we reach to this, as I said, the main summary. So at least get the only thing that you need to get from this video is just this fact, that for any observable Q, for example, the momentum, the kinetic energy, whatever, with the corresponding Hermitian operator Q bar. So we have three main properties. The first property, that Q has a real eigenvalues. Okay, so this is the property, we have already shown it in the linear algebra part. The second, that the eigenfunction are complete. So the eigenfunction of a Q, I should write of a Q, are complete. So that means any function you think of it can be written as a linear combination of these eigenfunction, any function in my Hilbert space. The second fact, which is I don't have the space to write it, so I will just describe it, that if we have two eigenstate of a Q, so let me say, for example, phi1 and phi2. So these are two eigenfunction or eigenstate of my operator Q, such that they have different eigenvalue, for example, alpha and beta. Then phi1 and phi2, they are equal to 0. They are orthogonal. So two eigenfunction with distinct eigenvalues, they must be orthogonal. Now we start to discuss about the spectrum of operator of Hermitian operator. So the spectrum is basically the set of all the possible of an operator. It's the set of all possible eigenvalues of the operator. This is simply the meaning of it. So we can think of it as a fancy way or as a generalization of the concept of the eigenvalues. It's called the spectrum. Now, physically, what's the meaning of the spectrum? It's important, maybe I didn't write it. Physically, it is all the possible value that we can measure. Okay, so all possible value that we can measure. Values that we can measure. So basically, what's the meaning of it? Let's assume that we have a specific operator. Let me call it, for example, again, the P operator, the momentum operator. So the spectrum of the momentum operator is the possible or the allowed value that I can measure. If you remember in chapter 2, when we have the infinite square wheel, we started with the Hamiltonian and we found what is the eigenvalue for it. So it was En. So what's the meaning of En? That all the possible energy that we can calculate it. So it's and that's why it's quantized energy. Okay. And speaking of that, so we have two types of spectrum. We have or spectra. We have the discrete spectra and we have the continuous spectra. The discrete spectra is the quantized one, as the energy that we have seen it. So we have the spectrum. So we have eigenvalue that we can distinguish between them. So we have, for example, phi 1, phi 2. So we can order them and we can see them and we can distinguish between them. Now, the main property of the difference between the continuous and the discrete spectra is that the eigenfunction of the discrete spectra has a physical meaning. So if you remember again, when we see them, we see the eigenstate to the state that have, for example, definite energy or different momentum. So they have a physical meaning and they are physically possible. They are allowed physically. Now, the problem with the continuous spectra is basically that if you have a continuous spectrum, so the eigenfunction of that operator, which has a continuous spectrum, it is not normalized. So if we take it, it's not normalizable. So if we take from -infinity to infinity, f squared, so it goes to infinity. So, but maybe you said, hey, you told us that they complete. I said, okay, yeah. They complete. So any function can be written as a linear combination of these. But these eigenfunctions of themselves, they have no physical meaning. So what we will do, like what we have done for the single particle or the free particle. We take the integration of these eigenfunction. This integration of all these eigenfunctions has a physical meaning. Okay? So we discussed about the completeness. The same thing, the orthogonality now, they have slight different definition. So the orthogonality now, they are equal to 0 if they are different. So we have the same thing. But now the inner product will go to infinity if they are the same. So this is called the canonical, this is called the Dirac delta function. It's important in physics and we'll use it, inshallah. We'll use it in this example. So this is basically the difference between the continuous and the discrete spectrum. Now, let's discuss the canonical operator, which are the position operator and the momentum operator, x and p. And let's solve this example. First of all, let's show that they are Hermitian and they have continuous spectrum. So let's solve A, that is spectrum. Actually, this is a special case of exercise that we already solved in linear algebra, that we have a real valid operator. Then if you multiply it, so basically the theorem says that if you have t and t of f, you multiply it by a specific function, real valid function, with this operator as a Hermitian. So this is just a special case, but let me show it here. So we need to compare f with x g. So we know we can take the integral. It's basically the definition. X star x g x dx. So apply the definition of the inner product. So now we can simplify. So we can write it as follows. So I can write x as x star because x is a real valid function. It takes a real value, and we have f star x gx dx, which is infinity x f of x or star g of x d of x, but that is equals to x f of x or x f. Let me just write g, which equal to x applied to g. That's it. So indeed, x is a Hermitian. Now we need to find what's the spectrum of x, and needs a little bit of work. So let me do it slowly. So let lambda be the eigenvalue of the operator t. So what does that mean? That means that the operator x, when we apply it on a specific wave function psi, let me say, it gives me lambda psi x. Now we need to do some analysis here, but before that, what is the operator? It's basically x lambda psi x. So here I just applied what's the operator x. because the operator x is just multiplied by x. You multiply the wave function by x. Now we need to do some analysis. So let me do the following. Take it to the other side. Psi x equal to 0. Now that's the following. If x equals to lambda, if x equals to lambda, or different from lambda, so we'll have this as a non-zero quantity, so that means psi is equal to 0. So this is for none when x is not equal to lambda. But here's the issue. When x equals to lambda, we have 0 times psi of x equal to 0. Now, I don't want my function to be 0 at this point. Otherwise, I will have a 0 vector. And remember that the condition to find the eigenfunction, that psi must not equal to 0. If you remember from the linear algebra, it must be a non-zero vector. So I need, at this point, so at x equals to lambda, psi of x is not equal to 0. So we take the following function, which is the Dirac delta function. So we consider psi is equals to x minus lambda. Of course, this is not a function. Mathematically, it's called distribution. But we take it, which has the following. So at x not equal to lambda is equal to 0. It's like the condition that we get. But when x equals to lambda, it is infinity. Now, what's the meaning of that? Basically, it has a very simple meaning physically. So physically, it has meaning, as we said, it's localized, so totally localized here. So the probability of finding the particle here is 1, and otherwise is equal to, it's identically equal to 0. So this is the meaning of the physical meaning behind the Dirac delta, or you can see it as mathematical meaning for it if you want, which is, as we said, as we seen from the previous argument. Now the eigenvalue for it, so the eigenvalue, the spectrum, has a continuous spectrum clearly. Why is that? Because lambda can be any real number, and that indeed makes sense because in principle, if you have a free particle, so you can find it anywhere. There is no, in our space, there is no specific discrete or specific restricted area where the electron or the particle could be. I'm speaking here in the free particle and in ideal case. So the lambda could be anything. There is no specific value for it. Okay. So now let me just show the completeness. That means that any function f of x in my Hilbert space can be written as the following. F of x can be as an integration from minus infinity to infinity, some constant, let me call it lambda. So of course here I will integrate with respect to the eigenvalues because I have continuous of them, okay, and the eigen function. So this is the structure, and we integrate with respect to d lambda. So this is basically of the completeness condition for in the case of the position operator. So any function eventually can be written as such. Now we go to part B. So, for the second operator, which is px. So part A. Now it becomes a little bit interesting. We need to show that it is Hermitian. So what we need to take f and we apply it to the second component, or if we want the opposite, so we apply it to the first component, and we need to show that this is equal to f when we apply it to the second component. So let's start with the left hand side. F of g is equal to what? Is equal from minus infinity to infinity, and be careful, it's equal to minus I h bar d over dx. If everything here we take it conjugate, then g dx, which can be simplified further. Now the conjugate of I minus I is I, so we can take it outside I, and also I will take h bar outside, so I h bar, and we'll have f d over dx, so f d over dx times g dx. Now I'll do an integration by parts, so which is the following h. So the integration by part, I will take u, or du, I will take it as df over dx which means that u is f, and I'll take v is g, which means that dv is basically dg over dx if you want. So if we multiply, so if we do it, we'll get f star g from minus infinity to infinity minus from minus infinity to infinity, and we multiply f star by dg dx. Okay, so what I'm doing here is basically a integration by parts. Now here's the crucial thing, that these must equal to 0. Why is that? Because we have seen it previously that if you have a function that is square integrable, so if we take this limit must equal to 0, as we go to infinity or minus infinity must equal to 0. So this actually, it has, as I said, a physical argument, not a clear mathematical argument. I searched for a mathematical argument, I didn't find. Some mathematician or some mathematical books, they just impose the condition. So they say, assume that we have this condition. But from a physical point of view, it's clear that if we have a function which is a physical function, so when we go to infinity, it must decay and become 0. So this is equal to 0, which can be simplified as minus I h bar from minus infinity to infinity f star, then dg dx dx. Now I'll take minus I h bar inside, take it here, so we'll get from minus infinity to infinity f star minus h bar d dx and f. But that is basically is equal to f b, the operator g, and we show that indeed this operator is a Hermitian operator. Now what we need to show, to find what is the eigenfunction for it and what's the eigenvalue. So we need to find b. When we apply it on specific state psi, we get, for example, let me call it again lambda psi x. Now what is b?
It's minus h bar d over dx psi is equal to lambda psi. If we rearrange, we get something like this, equal to I over h bar lambda dx. So this basically just the arrangement of this equation. Now if we integrate both sides, we get lambda is equals to I over h bar lambda x. Take the exponent, so of course we have a c, the constant. So if we take the exponent, we get psi is equals to some constant a, which is basically e over c, and a over h bar lambda x. So we notice again, this function has no physical meaning, because if we integrate from minus infinity to infinity, we'll not get a finite quantity. But if we take the linear, or the linear combination of it, we get a physical meaning for it. So first of all, let me do, So as we can see, these are the eigenfunction. I will just denote them by lambda. So, and lambda is a continuous variable. So, with lambda is continuous variable.
Now let's show that these are, so for any, these are orthonormal or orthogonal functions. So how to do that? Basically, we consider another one, which I will call it lambda, for example, the prime. So we'll have a e over h bar lambda prime x. Now we consider the inner product between these, so which equal from minus infinity to infinity a squared, and I will take, so I'm taking the star of the one on the left, so I'll have something like, write it in the red, so e minus I over h bar lambda x, because I'm taking the conjugate for it, and then I'll take the right one, which is I h lambda bar x. Now if we combine them, take e over h bar, and we'll have minus, I believe, take the minus here, and we'll have lambda minus lambda bar x dx. Now we use the hint that is given, where is it? That this integration actually is equal to 2 pi the 2 pi delta function of the q. So we'll get 2 pi. If 2 pi, I believe h bar also we have. Yes, 2 pi without h bar. Get here h bar. So h bar. So 2 pi h bar. 2 pi h bar delta lambda minus lambda bar. So if we take a square to equal 1 over 2 pi h bar, which in other words, we take a is equal to 1 over the square root of 2 pi h, then we have the following, that lambda prime, they have the orthogonality condition. So indeed these are orthogonal functions. More completeness, we notice an interesting fact that for any function in my Hilbert space, we can write it as a linear combination. So we have a, which is this constant a, I'll take it just outside, from minus infinity to infinity, some constant which depends on lambda, and then we have e I lambda over h bar x d lambda. So if we notice, we can think of it as this is as the Fourier transform of my function f with the Fourier inverse. So if you want to find the Fourier inverse, it is psi. I believe, just let me forget about the constant a here for now. From minus infinity to infinity, f of x e minus h x over h bar dx. So this is the Fourier inverse, and we will see in the future what's the difference between this function. Maybe in the future we'll see it or not, between this function and this function. Basically, this is the wave function, but in the position space, and that's why we have x. And here is the wave function. So this is c in the wave function, but it is in the momentum space. Lambda here, remember, it's the momentum. So usually it's more convenient to write b here instead of lambda. Okay. So basically both, they describe the same physics, but in different space.